Dear friends, welcome to a lecture on complex analysis. In this lecture, we shall study exponential form of complex numbers and how to express product, quotient, etc. in exponential form. Earlier, we have seen a complex number can be expressed in terms of polar coordinates r and theta. So, let z be a complex number which is in rectangular form or Cartesian form is written as x comma y, order pair x comma y, and in polar coordinates we have written this as r cos theta plus I sin theta. R is common. Now we shall use the Euler's formula to express this in exponential form. We have Euler's formula. Cos theta plus I sin theta or e power I theta is equal to cos theta plus I sin theta. So, using this formula the complex number z becomes. So, using this we get z is equal to see this is r and cos theta plus I sin theta is e power I theta by Euler's formula. R into e power I theta. So, this is exponential form of complex number because it is written in this in terms of this exponential function. Now, we shall have example for how to express a complex number in exponential form. For example, express this complex number z is minus 1 minus I in exponential form. For this purpose, we have to first consider z in terms of r cos theta sin theta, and we need to find out r and theta. So, let z is equal to minus 1 minus I, and that is first in terms of rectangular coordinates x and y. So, this is equal to x plus I into y. To find r and theta we get the value of x and y, and therefore, what is x? X is a real part and that is minus 1, and y is imaginary part, that is also minus 1. So, from this we know what is r. R is modulus of z is under root of x square plus y square, and that is square of x and y both are minus 1, square is 1, and therefore, this is root 2. Theta is, and theta is tan inverse of y upon x, but we shall write argument z which is a principal value of z, and that this is which quadrant we should note. It is third quadrant, negative x and negative y, and in third quadrant we have written in our earlier lecture formula for argument of z, principal argument of z, and using that formula we have in third quadrant it is minus pi plus tan inverse of y upon x. You please refer that lecture to get the argument z. This formula we have written in our earlier lecture, since xy lies in third quadrant, and that is equal to minus pi plus tan inverse of y upon x, minus 1 upon minus 1, and tan inverse, that is tan inverse of 1, and tan inverse of 1 we know is pi by 4, tan inverse of 1, and therefore, this is minus pi plus pi by 4, or which will be minus 4 pi plus pi, that is minus 3 pi divided by 4. So, this is argument of z, that is theta. Thus, we have obtained r and theta. Now, with the help of r and theta we should write the complex number in exponential form. Therefore, the exponential form of this number is, therefore, now z is equal to r e power I theta, and that is what is z is minus 1 minus I, and r is root 2 e power I into theta. Theta is minus 3 pi by 4. So minus 3 pi I divided by 4. So this is the exponential form of the complex number. Now we should note certain values of exponential function, as we have what is e power I 0. So this the problem is completed. This is the exponential form of this complex number. Now what is e power I theta? I into 0. But the Euler formula is important and famous formula. Using this we can easily write this complex number. What is e power I theta is cos theta plus I sin theta, and therefore this will be cos 0 plus I sin 0, and that cos 0 is 1, sin 0 is 0, so therefore this is 1. So what will be e power I into pi? That is cos pi plus I sin pi, and we know cos pi is minus 1, sin pi is 0. So e power I into pi by 2 is cos pi by 2 is 0, sin pi by 2 is 1. So the sin pi by 2, yes, it is 1, and therefore this is I, and so on. We can get these values. So e power 3 I into 3 pi by 2 will be minus I, etc. And thus the equation z is equal to e power I theta, and when theta varies between 0 to 2 pi, what this will represent? By these expressions we can see it will represent a circle with center at origin and radius 1. Represents the circle, or which is in earlier expression mod z is equal to r, mod z is equal to 1. The circle whose center is at origin, and radius is 1. So that means it will be this circle. And if this is theta, then the point here will be e power I theta, and as theta varies from 0 to 2 pi, the point will move along this circle. So similarly, the next equation we may consider as the equation see. We have seen this equation earlier, that is z minus z naught. Is equal to r, represents a circle with center at z naught and radius r. Its parametric equation is, or equation in exponential form is, z is equal to z naught plus r into e power I theta, and that will be this circle whose center is at z naught and radius is r. So this radius is r, and the point here will be this one, z naught, that is r e power I theta. So thus this angle is theta. Thus the equations can be written as equation in complex which is in rectangular form can be written in exponential form. Now we shall see product and powers in exponential form. First we shall obtain this product e power I theta 1 into e power I theta 2. This is equal. By Euler formula, what is the first exponential function? That is cos theta 1 plus I sin theta 1, and the second is cos theta 2 plus I sin theta 2. We shall multiply this. The product is as usual cos theta 1 into cos theta 2, and we shall multiply these two terms, which will be I square sin theta 1 sin theta 2, that is I square is minus 1, and therefore the real part of this product is cos theta 1 cos theta 2 minus sin theta 1 sin theta 1 sin theta 2. This is the real part, and plus I times the imaginary part is see, I is sin theta 1 cos theta 2 plus cos theta 2 and second part here, this we have written now, that is cos theta 1 sin theta 2, or yes, cos theta 1 sin theta 2. And now we see what is this. This is a trigonometric formula, cosine of theta 1 plus theta 2. Cos of theta 1 plus theta 2 is exactly this expression, and this is sine of theta 1 plus theta 2. Sine of theta 1 plus theta 2, sin theta 1 cos theta 2 plus cos theta 1 sin theta 2. And thus we have, again we shall express this in exponential form using the same Euler formula, which will be e power I times theta 1 plus theta 2. And thus what we have left side is e power I theta 1 into e power I theta 2, and this is equal to e power I theta 1 plus theta 2. That means this product obeys the usual law of indices, as we know a power m into a power n is equal to a power m plus n. The same is there, e power I theta 1 plus I theta 2 is there. And now with the help of this expression we shall write Z1 product of complex numbers, quotient of complex number and power of complex number. Let further Z1 be a complex number which is written in the form of exponential form as R1 e power theta 1, Z2 be another complex number R2 e power I theta 2, and let Z be general complex number, that is R e power I theta. Then we have first result, we shall write Z1 Z2, that is R1 e power I theta 1, R2 e power I theta 2, and R1 R2 are positive real numbers, so therefore this is R1 R2, and e power I theta 1 into e power I theta 2, and this is e power I theta 1 plus theta 2. So this is the product Z1 into Z2. Second thing, we shall suppose let Z is not equal to 0 and Z is written as R e power I theta. Then 1 by Z, or which is Z inverse. So Z inverse we can write multiplicative inverse 1 upon Z, we know, and because Z is not 0, and that is 1 over R into e power I theta, and this is 1 over R 1 upon e power I theta, and that is e power minus I theta using law of indices. And thus 1 by Z is written as 1 up, if Z is R e power I theta, 1 by Z is 1 upon R e power minus I theta. Third, further to get the quotient we shall assume Z2 is not equal to 0, and Z1 by Z2. What is Z1? R1 e power I theta 1, and what is Z2 is R2 e power I theta 2. So this is written as r1 by r2. These are positive real numbers, and this quotient is can be written as 1 over e. This can be separated, that is e power I theta 1 into 1 upon e power I theta 2. And further we can write this as z1 by z2 is equal to r1 upon r2 into e power, this as in this case, or here we can see we can multiply both numerator and denominator by e power minus I theta, and this becomes 1 and this becomes e power minus I theta, and therefore this is e power I is common, theta 1 minus theta 2, and condition is z2 is not equal to 0. Thus in this way the quotient can be expressed, and power of z can be now written as z is equal to r e power I theta, and therefore z raised to n is equal to r raised to n, e power I theta raised to n can be written as e power I into n theta. And now we shall write an important result which is known as de Moivre's formula. See, let this the same, let z is equal to r e power I theta, then z raised to n is equal to r raised to n e power I n theta. Put r is equal to 1, we get, now if you put r is equal to 1, what is the value of z? Z is e power I theta, put it here, and thus we get as z power n, left side is e power I theta raised to n, and what is the right side? Z we have put here, and r is 1 on both side, we are putting r is equal to 1 on both side. Right side r 1 is 1 raised to n is again 1, and e power I n theta as it is. Now we apply Euler's formula on both sides. On both sides we get, now what is e power I theta by Euler's formula? It is cos theta plus I sin theta whole raised to n, and what is the right side? Using the same Euler formula, here instead of theta it is n theta, and therefore the right side is cos n theta plus I sin n theta, and this result holds for every integer n, and that means n is 0 plus minus 1 plus minus 2 etc., and this is known as de Moivre's formula. De Moivre's formula. Now this formula is very important and useful. Now we can verify trigonometric formulas, or we can obtain trigonometric formulas from this. Now for example, see we have cos theta plus I sin theta for n is equal to 2. Raised to 2, put n is equal to 2 on either side. This is equal to cos 2 theta plus I sin 2 theta. Now what is the LHS? LHS we can expand this, a plus b whole square, a square plus b square plus 2ab, and see cos square theta plus I square sin square theta, that I square is minus 1, therefore it will be cos square theta minus sin square theta is the real part of this expansion, and what is the imaginary part or the middle term is plus 2 times I sin theta cos theta, plus 2 times I, or I shall write I separate, 2 times sin theta into cos theta. And what is the right side? Right side is this same, cos theta, cos 2 theta plus I sin 2 theta. Now equating the real and imaginary part, we get the formulae as, or the expressions as, equating real and imaginary parts. We get what is the real part on right side, it is cos theta, and this real part on the left side is cos square theta minus sin square theta, and what is imaginary part on right side is sin 2 theta, and imaginary part on left side is 2 sin theta cos theta, which are the trigonometric formulae. Known trigonometric formulae. So thus trigonometric formulae can be obtained using the de Moivre's formula. Now another usefulness of this exponential form is to express a complex number, power of a complex number in rectangular form, and we shall have one example. Express root 3 plus I power 5 in a rectangular form. Rectangular form means x plus I into y. For this purpose we shall express it in first in exponential form, and then we shall express it in rectangular form. And for that purpose we suppose let z is equal to, solution for this problem we shall solve it. Let z be this complex number root 3 plus I, and which is x plus I into y, and that gives x is equal to root 3 and y is equal to 1, and therefore what is r? R is mod of z, and which is under root of x square plus y square, and this is 3 plus 1 root of 4, which is 2, positive value we have to take. And what about theta? Theta is we shall have the principal argument, and this lies in the first quadrant, and argument z, and in first quadrant the formula is tan inverse of y upon x. For argument z, different expressions are to be considered for argument z, and this is tan inverse of 1 over root 3, and this is we know is pi by 6, 30 degree, or that is in radians it is pi by 6, because since tan pi by 6 is sin pi by 6, that is 1 by 2, and divided by cos pi by 6, that is root 3 by 2, which is 1 over root 3, and thus we have obtained theta, and therefore z is written in terms of exponential form. Therefore z is equal to r e power I theta, and that is r is 2 and e power I theta. Theta is pi by 6. This is expression for z. Z, or what is z is root 3 plus I. And now, but we are asked to find the expression for its fifth power. Now we shall take the power of this as fifth power. Root 3 plus I to the power 5, and this is equal to 2 into e power I pi by 6 raised to 5, or that is 2 raised to 5 into e power I into 5 pi upon 6, taking power of this exponential function. And again we shall express this as 2 power 5. We will express this power of e in terms of pi by 6, because we have e power pi by 6, twice e power pi by 6 is root 3 plus I, and we finally want to express this in terms of x plus I into y. Therefore I shall write this as e power I, and this can be written as in terms of pi by 6, pi minus pi by 6. See, 6 pi minus pi is 5, pi divided by 6, and again this is 2 power 5. We shall separate this as e power I into pi into e power minus I into pi by 6, and this is 2 raised to 5. We have seen earlier e power I into pi is by Euler formula cos pi plus I sin pi, which is minus 1. Verify this using the Euler formula, and this we shall keep as it is, e power minus I into pi by 6, or here it is, you see, e power I into pi by 6 is or twice of this is this one. So the term can be written at denominator with positive power, e power I pi by 6, and we write 2 here. This minus sign can be written separately. So that means multiply the numerator and denominator by 2. So this will be 2 raised to 6, 1 over 2 e power I into pi by 6. You know this simplification. Why we have written? Because we want to use this expression. Expression for 2 e power I pi by 6 is root 3 plus I, and we shall suppose this as 1. This is root 3 plus I power 5. Last step is minus 2 power 6 and 1 upon root 3 plus I. Now we shall rationalize the denominator. So, and we have to multiply by its conjugate, that means root 3 minus I, root 3 plus I into root 3 minus I. Rationalizing the denominator, and this further becomes minus 2 power 6 root 3 minus I, and what is the denominator? It is in the form a plus b into a minus b, which the product is a square minus b square. Square of a means root 3 square is 3, and square minus square of this I, that is I square, minus I square, that is minus 1, or which is 3 plus 1 is 4, and we can write this 4 as 2 square, and thus the final expression for this will be minus 2 raised to 6 divided by 2 raised to 2, that is 2 power 4, and 2 power 4 is 16 into bracket root 3 minus I. This is rectangular form of this complex number. So in this way, exponential form is useful to simplify powers of a complex number. Thus we have studied exponential form of a complex number and some examples. I hope you can understand this. The remaining part we will continue in our next lecture. Thank you for watching the lecture.